Hello students, welcome back. Let's go to section 3, selected topics from number theory, and this is going to be our preparations for what's to come. And in previous videos, both of which are optional, we went through division algorithm and the greatest common divisor, along with the rigorous proofs. Now, I hope everybody went through those optional videos, whether you understood everything or not. But in case you skipped, let's have a brief overview. The division algorithm goes like this. Given pair of integers a and b where the divisor b is strictly greater than 0, we can find a unique pair of integers q and r so that a is qb plus r, where r is greater than or equal to 0, but strictly less than b. So, the quotient and remainder exist and they're unique. A is called the dividend, b the divisor, q the quotient, and finally r the remainder. That's the division algorithm. Quotient and remainder always exist and they are unique. They follow these two properties, blue and green. The proof was really hard, but remember the result. Now, how about the greatest common divisor? Given pair of integers a and b, they exist a certain whole number, or equivalently speaking, a non-negative integer d, such that d is a common divisor, that is, d divides a and also d divides b. And finally, d is a linear combination, ax plus by form, for some integers x and y. So we have these three conclusions, green, blue, red. Not only that, this d satisfies these three properties. Its whole number, green, so greater than or equal to 0. Okay, that's trivial. It's a common divisor, which I already talked about here. And finally, it's the greatest common divisor in a sense that if there is any other divisor, any other common divisor, then that common divisor divides d. And d is non-negative, so it has to be the greatest. And it has something to do with this linear combination property, even though it's not that obvious. And this is the greatest, so there is only one such element like that. So we can call d the greatest common divisor because there's only one such number. As a matter of fact, here we proved only existence, but as a matter of fact, it turns out there exists only one such d. The existence is unique. And the proof, of course, was really hard, so I'm not going to go back and talk about it. But in any case, remember all these. The GCD is greater than or equal to 0. It always exists uniquely, and it's a common divisor, and it satisfies this linear combination for some x and y integers, ax plus by form. And that gives rise to somehow the greatest common divisor. That is, every common divisor divides d. Okay, all right. Keep those in your mind, and you may not be able to prove any of those, but you should remember all those conclusions, and you should be able to use those. This one is not going to be too difficult to use. This one may be a bit of a challenge, especially the one related to this linear combination. So let's do an exercise here. If two integers a and b are, wrong wording. two integers a and b are said to be relative prime if the GCD is 1. The following result is known as Euclid lemma. So if a and b are relatively prime, that is GCD is 1, and a divides b times m, then a divides m. So a and b are relatively prime, so they do not share any prime factor. So everything in A must belong to M if you know prime factorization. But there's a problem. The proof of prime factorization is really, really hard, and it requires these kind of things. So that's not the right way to prove it. Let's prove it using the greatest common divisor, especially this linear combination form. How do you do that? Well, here's a sketch. Let's begin with this observation. GCD is 1, and that's the greatest common divisor. So 1 is ax plus by for some integers x and y. Remember, I just used this red property. Okay, how does that help? Well, I want to prove something associated to m. So what I'm going to do is multiply m to both left-hand side and right-hand side. Like this. Multiply by m, and then if I break up the parentheses, I'm going to get max plus mby, etc., etc. Does it help? Well, from here, make an additional observation that a divides b times m. So b times m, that's going to be a special quantity that I have to work out. It's hard to read this. Let's make it purple. So this m times b is divisible by a. So we can rewrite this as max is all set. And then mb is divisible by a, so anything. S times a plus y. Kind of like that. Does it make sense? This mb is divisible by a, so something times a. I wrote it like that. And then now it's pretty clear. I can factor a out of here. So what do we have here? A times a certain integer. Consequently, a divides m. The conclusion follows. Here's a full proof. Instead of SA, I used AQ. This purple, that purple. Yeah, everything is here, so let's go back to where it was. That completes the proof of Euclid lemma. And also, please remember the result.